Our next speaker is Glen Waychunas. He is visiting faculty member at Caltech in their Division of Geological and Planetary Sciences, and he's a scientific associate at Lawrence Berkeley National Laboratory. He has over 200 journal publications, and about 15 of those feature in mineralogical luminescence. And this is his area of specialization. His current research is on determining activators and luminescence mechanisms in minerals, including characterization of associated electronic defects. So Glen is going to talk to us this afternoon about rare earth elements as activators, and particularly in apatite, fluorite, and calcite. So with that, I'm going to turn it over to Glen.
Thanks for inviting me, and thanks for the introduction, Julian. I'm going to discuss luminescence in minerals due to rare earth elements as activators. And I have a couple pictures right on the first slide. Pectolite's on the left. It's from Mount St. Hilaire. It's about a 5-inch specimen. You can see it's got a nice pink luminescence. Maybe other people think of a different color there, but my eye sees it as pink. There's also calcite there that fluoresces in orange. This specimen is activated by two rare earths mainly, europium and samarium. We'll talk more about what's going on in this later on. But of course, whenever you have any rare earths, you probably have all of them in the sample. And so it's always a little more complicated. The center one is catapleite from Mount St. Hilaire. Probably guessed by now I like Mount St. Hilaire minerals. The catapleites are little hexagons. They're beautiful little crystals. This is also about a 5-inch specimen, and it's activated by uranium as the UO2 ion. So it's a complex. It's not just the uranium, which is 6+, but it's a complex that's in the structure of the catapleite. On the right is apatite from Pakistan. You'll often see apatites that fluoresce this color, sort of a bright yellow, really bright saturated yellow. It's interesting because you could get this yellow from either manganese in some cases or from dysprosium. And this particular one has quite a lot of dysprosium, and dysprosium is a very important rare earth activator for yellow in minerals. You've probably seen this today at least another time, so I won't dwell on it, but I want to indicate what the rare earths are. And the periodic table there is on the right. And we usually think of their rare earths in the largest grouping as being both the lanthanides from lanthanum to lutetium and the actinides from actinium to lawrencium. And some people lump in scandium and yttrium, and those are indicated there as sort of like a pale yellow or a light brown. But actually, for most intents and purposes, the most important rare earths for almost all technological principles and in minerals are really the lanthanides. And the one exception to that is uranium, as uranium 6+ or uranol, that activates a lot of luminescence in minerals. Now, on the left-hand side, there's an indication of where the rare earths go. If you see the table that's circled there, or the column in the table that's circled, you'll see that there's the ionic radius of the rare earths. These are all trivalent rare earths. Your rare earths could have several different valence states, but the most common lanthanide valences are the trivalent state. You can see that the distances, the ionic radii go from about 1.04 angstrom to about 0.86. These are very similar to sodium and calcium. So in general, that's where these elements go. So any calcium mineral, any sodium mineral can have significant rare earths. But there is the problem of charge balance. And on the upper right, you can see a couple ways that the charge balance is worked out. In apatite, it's the first two little equations there. You can have rare earths substituting for calcium, but you also substitute a silicon for a phosphorus. So its charge balance is maintained in apatite that way. The second one is a rare earth and sodium substituting for two calciums. That also maintains the charge in the structure. Next one is substitution in fluorite. If you have an oxygen substituting for a fluorine, that's the O2 for the X, you can also get charge balancing with the trivalent rare earth. And finally, at the bottom, that's an interesting one. Two rare earths can substitute for 3 calciums in a structure, producing one calcium site that's vacant, or there has to be some way to make that site vacant. We think that this is an important feature actually in carbonates when there's some radioactivity that produces some calcium vacancies. And so then you could get rare earth substitution. I'm not going to say much about that. It's a whole other talk that has to do with the Terlingua, Texas calcites, but we'll get to it sometime. So anyway, we'll go on. You've probably seen the right-hand side. This is the abundance of the rare earths, and I'm not going to dwell on it. The rare earths are in the lanthanides are in the blue, and you could see they're normalized to abundance of 1 in this plot, as a function of atomic number. you could see they're actually not that rare. I mean, they're rarer than the really common elements, and they're rarer than some of the things that we see pretty commonly used, strontium, zinc, manganese. But they're not as rare as cadmium. They're not as rare as silver. They're not as rare as lead. They're actually fairly common. And some of them, like cerium, are really fairly common. And that's the reason why cerium oxide is not so expensive and it could be used in polishing by the pound. So it's quite interesting. On the left, you see a graph which shows the electronic configuration of the rare earths. That's the third column, I guess. And you could see that there are all 4F elements. These are the lanthanides again. The actinides would be 5F. And you could see they have different numbers of F electrons and pretty much the same number of S and P electrons. And the transitions we're mostly going to see in these elements are going to be between these vacancies in the F shell. It'll be a F electron going to another F electron position. So we call them FF electronic transitions. However, cerium and samarium and a few of the other ones that can be divalent, then they'll have other sorts of transitions involving the D shell. So they have DF transitions, and that makes them distinctively different. So here's the basic idea behind fluorescence. I'm not going to do much in the way of fancy diagrams today. The rare earths are kind of complicated, but this is a pretty fundamental diagram. This is actually one I put up together for chromium. It shows the chromium fluorescence levels, but it doesn't matter. The whole idea here is that you have a ground state. This is the lowest possible state of the ion, whether it's whatever atom it is, manganese or chromium, neodymium, samarium. And then you have excited states. There's first excited state, the second, the third. All of these can be excited by an excitation from the ground state, by light. In this particular diagram, there's an excitation here is ultraviolet or blue light. An excitation here is green light, and this is an excitation which is red light. And this emission here is in the red. So in the case of ruby, all those different types of light will produce the red emission. An excitation up to this level, there's a loss of vibrational energy to this level. There's a loss of vibrational energy to this level. And then this level, the first excited state, it has no way to release that energy as anything other than a light photon. And so that's why you get the light emission. So this is generally what you see. The first excited state and the ground state are the ones you're concerned with in talking about the luminescence. If the first excited state changes in energy for some reason, like if it's sensitive to the mineral site, then you're going to change this light emitting energy. One important thing from this diagram is to note that these arrows for absorption, whether it's red or green or blue, are all longer than the light emission arrow. There's a shift in energy. The light emission is always downshifted in energy. We call that the Stokes shift. It's a necessary aspect of the luminescent process. Okay, now let's look at the trivalent and divalent elements. I'm sorry, this is a little fuzzy. I pulled it off the internet. I wanted to find a better one, but it's good enough because it shows the bands that are colored of the different rare earths. These are all trivalent rare earths. This is the wavelength they emit at. And you can see that trivalent samarium emits in the deep red, europium 3+ in sort of the more of the orangish red or orangey red, dysprosium in the yellow, terbium in the green. They do have other emission bands. I'm not going to talk about that. These are the principal bands. But what you can see here is that the trivalent rare earths emit particular colors, and those colors don't change very much. And the reason they don't change very much is because these are F to F transitions. And the F electron shells are buried inside these atoms. They're covered by D shells and S and P shells. And so as a result, those electron states are not altered very much as you go from one mineral to another. So consequently, the emissions are always about the same color. Not quite, there is some influence, but they're about the same color. So that means that we can really identify these, if we can get a good spectrum of them, we can identify which elements are responsible for the luminescence. That's a whole different story for the divalent rare earths, like europium, samarium 2+, a few others. In that case, they vary according to the crystal structure. This parameter down here, this is the ground state, and there's two excited states of europium. And this is called the crystal field energy, and it's increasing to the right. Crystal field energy responds to the electric field created by the site where the atom is. If the atoms are, if there's 6 coordinated, the field is stronger than if there's 4 coordination, 6 oxygen versus 4 oxygen. And if the oxygens are closer in an octahedral arrangement, 6 coordinated, the field will also be stronger. So anyway, consequently, if you have a larger field, you will see some variations of these energy levels. This is a D level. So it's going to be affected by that field. The F levels are not. So what happens for europium is that very weak fields, you would see this problem in fluoride, you're going to have ultraviolet blue emission as you're getting this transition. But then as you get a field which is stronger, like in calcite or in wollastonite, this second excited state drops in energy until it crosses over, and it's now the lowest excited state. And it keeps dropping as a function of this site parameter. So you could have any possible color. You could have red if it's down here, if it's a very strong field site, or you could have blue if it's a relatively weak field site. So europium is a popular activator in phosphors because you could pick a phosphor, you could design a phosphor that has a structure that gives you exactly the kind of site you want, exactly the kind of field you want here from the atoms around the europium, and you can get any color you want. And it's also pretty efficient. Okay, now, one consequence of these guys is that they all have particular absorptions as well as emissions. So we could use different wavelengths of ultraviolet or even visible light to observe them separately. And I'm going to show that in the next couple slides. This is an example of leucophainite, gadonaite, and microcline from Mount St. Hilaire. Now, there's actually several other minerals. It's got about 8 minerals in it. So it's sort of a typical messy Mount St. Hilaire specimen. In physical light over here in the upper left, you can see the leucophainite crystals. They're sort of yellowish. That's actually a coloration due to rare earths. And the rest of it's kind of fuzzy, hard to see. But these are the different wavelengths that I could use to excite it. If I use 310 nanometers, we call that middle wave often, ultraviolet, or something around 310. We preferentially excite the samarium 3 plus, in the leucophainite, or some people say it's called leucophainite. I'm not sure what the pronunciation is. We also excite some europium, and the combination gives you a pink. You have sort of a red-orange from the samarium. You've got from the europium 3 plus, and you've got some 2 plus from the europium, and you get this color. The blue and the orange together give you the pink. If we use 365, we preferentially excite only the europium, and then you see much more of the blue color. There's still other colors coming in because this thing has more than just 2 rare earths. It has them all, and they're all contributing a little bit. But basically, those are the major ones contributing. Finally, if we use a shortwave UV, we activate iron that's activating luminescence in the microcline. We're seeing the uranyl activated more in the gadonaite, and we're seeing the leucophainite or leucophainite react too. So you get this very nice blend of colors. And actually, if under a microscope, you can see 3 other colors in this due to still other minerals present. So it's quite interesting. But it shows you how we can use the different wavelengths to separate out some of these phenomena. It's also just fun to play with. Here's another example of the same thing, which is a little bit of a stranger mineral in some ways. This is dodecahedral fluorite from Peru. This is an old specimen from an old collection, probably 50 years old. This is from the same quarry that they mine, or part of the quarry where they mine all the nice pyrite. You can see the dodecahedral forms. This specimen's probably about 5 inches across too. I'm broken record here. Most of these specimens are about 5 inch. If I excite with long wave UV, that's 365 nanometers. It preferentially excites the UV2 plus, which is here. And the UV2 plus is replacing the calcium. It's a very good fit. And you get this very pleasant blue emission. And fluoride generally fluoresces blue from europium. We know about the fabulous fluorides from particularly Great Britain that have incredibly bright fluorescence from europium 2 plus. And that's another example. But something else about these things is happening, which is unusual. If you look here, you can see some spots which are a little paler. And then if I go to shortwave UV, those spots light up sort of a reddish pink. So what's happened here is we have zonation. It's the original form of the crystals are actually, it turns out if you study this under a microscope, they're actually cubic. And they go from cubic to octahedral to dodecahedral. It's quite interesting. And they form different zones. I didn't want to section one of these things to show you. It's a nice specimen. It's a kind of a rare specimen. But you now have activating the europium is still giving you blue over here, but you're getting this pinkish effect from orange red coming out of the samarium 3 plus. There's a third thing going on here, and that's at the surface of the crystals. They have a light coating. I don't think it's in the fluorite. I think it's another phase. I need to investigate that, which is some sort of a uranium activated process. Where's my pointer? Yeah, some sort of a uranyl activated process that lights up pretty well here. So this is a very interesting specimen. I've only seen 2 specimens of this type in my life, and I have one of them. The other one was in a museum, so it's hard to find this up. But the dodecahedral itself form is not too rare. The other thing that rare earths are interesting for, particularly interesting, is that they sensitize other rare earths and other metal ions into fluorescing. That says they act as what we call sensitizers. There's 2 ways they do this. One way is this diagram here on the left, and I apologize for this being a little complicated diagram. It's not too bad. This is the wavelength, and this is the absorption peaks or the absorption profile of some element. Let's say it's a rare earth, and it has emission next to it. There's a shift because there's a Stokes shift. It has to be at lower energy. Now here's a second element, a second rare earth. Its absorption is here, and its emission is here. It has a smaller Stokes shift. The key thing is that the emission of this one rare earth overlaps the absorption of the other rare earth in this green region. That's all you have to have. So the fluorescence of this rare earth is exciting the fluorescence of this rare earth. This is called FRED exchange, for fluorescence resonance electron energy transfer. There's also other names to it. One of the things about this is it can happen over a long range because it's fluorescence. So one atom could be, 30 atomic units away, 30 angstroms away, 40 angstroms away from another one, and it will still affect it in this way. So things all throughout the structure, even if it's pretty dilute, can operate this way, although it's not as strong as this other method. The other method over here is called resonant exchange. And what this is, and I apologize for the funny diagram, if you have a transition in one rare earth like samarium 3+, that's just at the energy of an absorption in another rare earth, very close, then they can resonate if they're close together. It's the same phenomena you would get if you had a 2 coils of wire and a capacitor, and you form 2 resonant circuits. And one was you started one resonating, the other one would immediately pick up that resonance and resonate with the other one. There would be very strong transfer of energy. That's what happens here the same way. For this to happen, they have to be very close together, practically adjacent. And some people call this a form of what's called direct exchange, while the FRED is not direct, it's indirect, it's there at greater distance. But anyway, these 2 things can happen quite a lot with rare earths. They're responsible for a lot of energy transfer to other atoms. In the case of the FRED, you can have another rare earth over here. So you could go one excites the other, excites the other, excites the other. They call that cascade fluorescence. And it's also happens a lot with rare earths. One of the cases which I didn't have a good slide of, I wanted to show you what happens in Rogerly fluorite or any green fluorite. Green fluorites are colored by samarium 2+. It's a pretty strong absorption, D to F transition, but that also strongly absorbs radiation and sends it to the europium. So the areas that are the darkest green are often the brightest fluorescing ones because of the samarium is co-activating the europium. And there's some fluorides that have come recently out of Colombia that are mostly white with little splotches of green, which is due to the coloring by samarium 2+. And that's exactly where all the bright blue fluorescence is. I have one of those, and I was going to show a picture of it, but I couldn't find the specimen. I mean, I have a lot of specimens. It's somewhere buried in my collection, but it's very interesting. So that's another case of the energy transfer between rare earths. Here's another example. I put this, forget about this. I'm not going to talk about the concentration effect except just one sentence. This is calcite from Elmwood Mine, Tennessee. I mean, I think everyone's seen these beautiful crystals. This is about a 3 or 4 inch crystal. It has fairly decent terminations on it. Often they have the nicked edges. If you put long wave light on it, you see this beautiful orange luminescence. Normally, this is manganese. Normally, you would only see this from shortwave. But what's happening is that it has a considerable amount of europium. The europium is picking up the energy from the ultraviolet and sending it to the manganese. So we have manganese emission, but europium absorption. If we excite at 296 nanometers, actually should be 295, then we'll see the europium itself. We don't exchange much energy with the manganese at that energy. And we can see actually a nice play of colors here. There's other things going on with rare earths, but that gives you an idea. So the calcite from Elmwood is an excellent example of this energy transfer and co-activation of rare earths that happens a lot, particularly with manganese as the receiver of the energy. Here's a couple of examples for fun. This is a pinkish purple. It doesn't come out so well in the photograph. It's actually a light purple colored mass of apatites from Afghanistan. It's about 6 inches across. A beautiful specimen. It was expensive, I have to say. But I got it because the fluorescence is amazing. Not only is it a night crystal, but the fluorescence is amazing. In this case, we could we'll use several more wavelengths. This is what happens at 405 nanometers. This is the blue laser you often see sold. You can excite the luminescence with that. It kind of looks blue to the eye. You get some blue reflectance from the sample. And so I'm using a filter here to block the reflectance of the excitation. And when you block that, you can see it's a beautiful yellow with some other pastels in it. This is mostly dysprosium with a little bit of manganese added to it in this particular apatite. If we go to 365 nanometers, we begin to see the europium coming up, but we're still getting the dysprosium as well as other things. If we go to 310 going down, you begin to see the europium is overtaking it. We're seeing less of the dysprosium and most europium. And if we go to 254, now we're getting some direct excitation of the manganese with the shortwave ultraviolet, and we're still getting some of the other things happening. So you got this complete blend of colors. The processes are going on here because, as I said, other rare earths are also present and they're all contributing. But at least you can see some major differences as a function of wavelength. And it's just a lot of fun. Makes a hobby interesting and thought-provoking. Here's another example that's pretty commonplace for as an example of rare earth emission, and it's in scheelite. Scheelite usually fluoresces blue under shortwave ultraviolet, 254, and sometimes it doesn't do anything else under other wavelengths. But some of the scheelite crystals, particularly from the Taihu mine in South Korea, I'm not sure how to pronounce this, have a beautiful red-orange luminescence, largely due to samarium 3+ with a little europium 3+. And it's actually quite bright. It's surprising how bright it is. And every little feature is visualized due to it. This particular specimen only has these two colors, but there are some scheelites that if you change the wavelength, you can see other colors as well. Some of them are bright yellow, bright red-orange, and bright blue under shortwave. This is, of course, due to tungstate, the WO4 group. This is a different kind of activator because it's not just the tungsten, it's the whole WO4 group that does the absorption and the emission. That's another story about the details of that. It's a very strong emission. And here's a few more to look at. These are all apatites from my apatite chapter I wrote, I don't know how many years ago, for the reviews in mineralogy with the MSA, and shows a bunch of different apatites with different rare earths that have been determined spectroscopically. They're the dominant rare earths. They're not the only rare earths. From Greenwood, Maine, you have a lot of europium 3+ in the apatite. Again, it's dominating, but it's not the only one. They're all there. And the matrix is dominating with EU 2+. So then you have this beautiful sort of a reddish, pink reddish, orange reddish, and you have the violet bake. This is a relatively small specimen, it's maybe about 2.5 inches. From Durango, Mexico, we've probably seen these apatites around for a while. They're sort of yellowish. The yellowish color is due to rare earth absorption. And there's hyalite opal activated by uranium. This has got europium, cerium. Cerium is a very important, cerium 3+, very important activator. It's it's usually present in pretty high concentrations. And so it often activates sort of a near ultraviolet purple luminescence. And it also transfers energy to other rare earths. So it's a very important rare earth to explain luminescence phenomena. This is a pegmatite from Ridgefield, Connecticut. It's actually apatite and merging into autunite. Autunite is in fact a apatite. And so you could actually have replacements that allow them to sort of be grown together, intergrown. And so you have uranil on the green parts here. You also have manganese and probably other rare earths present as well. From Pakistan, this is a large single crystal. This particular crystal has a lot of electronic defects, so it has really good phosphorescence or afterglow. But mainly it has an awful lot of dysprosium 3+, and so it has that beautiful color that I talked about earlier. It's also got manganese 2+ present as well. So there's sort of a baseline that's a little more orangey. From Jakobsberg in Sweden, this is a sample I collected myself probably about 20 years ago. This is John Baumite. I'm using the nature of the fluorescence as a dictator of what the phase is. It's not true that you can really tell apatite, John Baumite from spavite, from this or that turnerite by the color, because it depends on what the trace impurity activators are. But in this case, you have a sizable amount of europium 3+ and samarium 3+, and they're giving rise to this beautiful pink. And the matrix is largely calcite. You can see it's bright. It's calcite, which is fluorescing very brightly here in long wave, because again, it's co-activated by the rare earths. This is Franklin, New Jersey apatite. It's got manganese, doesn't have much in the way of rare earths, and so you see the sort of basic color you'd expect for manganese in apatite in both sites. And then there's also fluorescence from the calcite, nice red, and willemite, of course. So I've covered these. Okay, zonation. We see zonation of all sorts in minerals all the time. We see physical zonation. We see phantoms, which is sort of a type of zonation. But we also can see very nice luminescent zonation when, in fact, from a physical point of view, you can't see much. Actually, in the case of this sample, you can see that there's zonation in white light. This is an apatite from Penasquara, Portugal. And this is a big specimen. It's about almost a foot across. Very large crystals. You could see it looks like there's something a little different on the ends of the crystals. And sure enough, when you put it under long wave light, you can see that it's got sector zoning. The body of it is sort of a yellowish. I don't know if I would say it's got much of other colors in it. When I go to 405, however, you can see how it lights up. Whoops. Again, that's from the dysprosium and also a contribution from a manganese. What we think is happening there is that we have zoning something like this on the side of it. It's caused by, as the steps are growing, forming the surface during the growth phase, you can get particular attachment on these different types of sites, in fact, by different rare earths, and also maybe by different other impurities. So in fact, it's a phenomenon that's caused by the uniqueness of the structural aspect of the growing surface. And there's a paper by Rakovic and Reeder in GCA 1996 explains this very nicely. It's a very nice paper. Enjoy reading it several times. This is what gives rise to selective uptake of particular activators during the growth. That's what results in this. And it's actually a pretty common phenomenon. There's plenty of minerals that show fluorescent zoning. I think everyone's probably seen gypsum crystals that show the zoning, but in that case, the zonation is caused by different charges on the surface and the uptake of organics during growth. Okay, sort of last major topic here are the time scales of luminescence. I mentioned that the FF transitions are different from the DF transitions earlier on, the trivalent versus the divalent. And they're different in an important way. The DF transitions have a lifetime of the excited state that's relatively short. So you could speak of this as being fast. Whereas the FF transitions, because it's an F to F transitions, I won't explain why, these transitions are somewhat forbidden quantum mechanically. So it takes a longer time for that to happen. And I can illustrate this with this diagram. This is a diagram, the time is on this axis. This is the overall intensity. And here's whether the UV is on or off. So you can put UV on for a while, then I turn the UV off and you just wait and we watch. If you have a fast process, a short lifetime, the fluorescence will quickly come up and reach a steady state. And then when we turn the UV off, it'll decline quickly and then slowly come back. Not slowly, but come back pretty quickly. If, however, the lifetime of the excited state is long, so once we excite it, it takes a while before it can de-excite. It's forbidden. It takes a while. It waits. It has to keep trying to emit, and finally, it's able to figure out some way to emit. It's a whole other talk about what's going on there. But believe me, that's what happens. In that case, it ramps up slower, and when we cut off the UV, it ramps down slower. So if we have a way to somehow separate where we watch the intensity, we might be able to separate out these two types of rare earths. And that would be a boon. You wouldn't have to do it with really wavelengths, but you can do both wavelengths and timing. And that's what's done here. And this is one of my collaborators in a number of projects. He's probably the world expert in luminescence in minerals today. And that's Michael Gaft in Israel. But he's a physicist, and he's pretty much developed this technique of using laser time pulses to understand the lifetime characteristics of luminescence. And here's how they do it. This is the same diagram you saw before, but instead of exciting the luminance, putting the UV on or the laser on for a while, we just have a brief pulse. And then we wait a while and we pulse again, so that we do it again and again and again. So in this pulse, you get the relatively fast luminescence decay, and then here's a long luminescence decay. And then the whole thing happens again. Now, what you can do is, if you have a setup like this, is you also have a very special detector that you can turn on and off very quickly, very high-speed detector. And you could also wait for a while after the laser pulse before you turn it on. For example, in this case, it's turned on here and then turned off there. So what does that detector see? it only sees this luminescence because it's too slow for this luminescence. So you can do this in all sorts of ways, and you could do different wavelengths, and that's what's shown here on the right. This is a single apatite specimen where they've changed this delay period here and the gate period, which is here, in different ways, and they can separate the luminescence in this case quite wonderfully. Here they can see cerium in the number 1 apatite site and a little bit of the number 2 site, and over here with slightly different characteristics, they can see them in both sites. It's interesting. I mentioned that cerium 3+, it's an FF transition. It's not too sensitive to the structure around, but it's a little sensitive, just enough so you could separate out something like this, because the 2 sites are quite different in coordination in apatite. If we go to an entirely different delay, this is actually a faster one. We can see the europium and pretty much nothing else, the europium 2+, because it's a faster condition. And if we go out here to a much longer one, we'll see the dysprosium, which dominates that, and also some europium coming out here. So here we have a way that we can separate the rare earths from a scientific standpoint. Now, you can't actually see any of this. It's all recorded. You can't do anything to see this with the eye, although it might be possible, I guess, if you had some sort of a goggle that also opened and closed very rapidly, you could actually watch this pulsed experiment and see only whatever the detector was seeing. But I don't think that's possible. But at least we can do this analysis, and it's due to the fact that rare earths have this unique range of lifetimes. So anyway, that's pretty much what the talk is. I have another slide of some pretty minerals to show you after this one. Now let me go over what I've talked about, and I hope it's been not too fast and pretty understandable. Trivalent rare earths tend to produce similar luminescent colors regardless of the mineral structure. The transitions are forbidden with longer excited state lifetimes. There are 4F to 4F transitions. Divalent rare earths have luminescent colors very dependent on the mineral site, but they do have shorter lifetimes. They're generally 5D to 4F transitions, so a different kind of electronic transition. Rare earths can substitute in structures by several schemes. They usually substitute for sodium and calcium, but as you saw back there, there's another couple schemes that can happen, like for fluorite and calcite. Now, rare earths can also act to excite one another. That's called sensitization by transferring energy. They can sensitize transition metal activators like Mn2, besides just other rare earths. And they're actually a very important source of sensitizing Mn2+. That's why Mn2+ is just commonly available, but it's a very poor absorber of ultraviolet. That's why we commonly see luminescence from Mn2+. In some cases, it's also sensitized by lead. That's true at Franklin. So there's another sensitizers. Finally, high concentrations of rare earths, they can quench each other's luminescence. I actually didn't mention this to now, I forgot about it, but just when you have sensitization, you can transfer energy into another rare earth and it will fluoresce. You could have the energy of the fluorescence transferred out to some other rare earth, stealing the energy so that you get less fluorescence. You get resonance transfer that way, particularly if you have higher concentrations of rare earths. And that's why, in general, rare earth minerals have almost no luminescence. They're too concentrated. They're self-absorbing the luminescence. They're transferring the energy out. Eventually, it all gets lost to heat and thermal vibrations. So generally speaking, you're looking for low dopant levels of rare earth elements and something to get good luminescence. And so that's why I mentioned this down there. So that's the end of the technical talk. I got one more slide. And this is a few other goodies from my collection. Here's delhaiolite, which is a rather unusual mineral. It's actually high in the S2- ion, which fluoresces a bright orange. And here I'm selecting out only the rare earth part. It's probably an interesting combination to add the orange to this, but I'm not activating that with this wavelength. Then here's some pectolite from the Kola Peninsula. It's actually present with villiumite, VILLIAUMITE, sodium fluoride here. So that's an interesting one. The villiumite actually does fluoresce, but you need a different wavelength to see it. Here's some natrolite from Mount St. Hilaire, activated by urano. And these guys act like little fiber optics, and that the light comes right down the end of the tubes. It's brightest at the end if you look down the end of the tubes. These are great specimens, and they're actually fairly common. Although I'm collecting, unfortunately, is very limited at Mount St. Hilaire these days. There's a lot of specimens that are in old collections. Over here on the right is about a 1-inch crystal of apatite from Bolivia. It's a beautiful crystal. It's colorless. Again, it has dysprosium, which gives you this very nice yellow. And if you go to long wavelength, you see that you activate the europium and a little samarium. And these crystals also have sector zoning. It's unfortunately not well shown here. You could see it with the naked eye. It's kind of subtle. It's also got some beautiful zoning. Particularly the Bolivian crystals often have wonderful sector zoning of luminescence. And then finally, this right here is a grelite. Most of grelite that you hear about comes from the Grenville province in Canada, but this is from Tajikistan, and which I forgot, didn't spell right here. So this is a pretty big specimen, and I got this a while ago when specimens coming out of Tajikistan were not that hard to find, particularly from some of the Russian dealers. And that supply's pretty much, I think, been cut off now. But it's a beautiful emission. It's got manganese emission, and it's also got a large set of the rare earths, particularly europium and samarium. And this also has baratovite and pectolite and other minerals in it too. So this is gorgeous when you hit it with several different wavelengths. But here I'm just trying to emphasize the rare earth emission. So that's it for the talk. I'm looking at the time. I've done about 45 minutes, which is or 40 minutes, which is what I wanted to do. I'm willing to answer questions on any of this, or if anybody has something they'd like to tell me about that's interesting, I'm all ears. All right, thank you.
Thank you very much, Glenn. We do have a couple of questions. Bob?
The last comment about the quenching was kind of interesting, and I was just wondering if the rare earths could quench other, the excitation from other things, say, one of the other, like chromium or one of the other elements, or is it just a rare earth quenching?
No, they can quench anything. They can quench it by several means. Both of those mechanisms I mentioned for transfer of energy work. So you can quench by means of that fret. In other words, you're trying to get the fluorescence out of, say, manganese, but there's rare earths there and they soak up the fluorescence, and they either fluoresce themselves or they change it into heat. So, and yes, they can. Most minerals don't have really high concentrations of rare earth unless they're a rare earth mineral, specific rare earth mineral. So you don't see too much of that because the average spacing of the rare earths and the other ions are too far. But it does happen, and I can't think of really a great example, but it can happen, and of course it must happen. So,
hi, Marcus here. A question about the scheelite fluorescence, especially there are these scheelites which are very dark red, and I don't know where I picked this up, but I couldn't get that source again about the idea that this is actually samarium, and it's actually a quasi-daylight fluorescence, that it's actually excited just by the blue side of the spectrum and then emitting around 600 nanometer, which would give that deep red appearance. Is that something you can comment on? Have you heard of this or know more about that part?
well, I don't know. I don't know if I've heard all of your question. Unfortunately, the scheelite has more than one rare earth. Of course, it has several. And some scheelite, for some reason, doesn't have too much. I mean, scheelite's a pretty high temperature mineral, and that seems to have some effect on the rare earth concentrations. And so I think if we look at scheelite formed at the lowest possible temperature versus scheelite formed at the highest possible temperature, we might see a difference. I'm not a petrologist, but I have a lot of scheelite in my collection. Some of it doesn't show any obvious rare earth emission, but some of it does, and some of it's pretty spectacular. As I mentioned, there's some of it that is yellow under other wavelengths. So I haven't heard of any other specific mechanisms like that. I mean, this one I showed you is got quite a large amount of samarium 3+, and it has the other rare earths as well. But that's what dominates. I have heard of other scheelites that fluoresce like very orange, and I don't have them, and I haven't done any spectra on them, so I don't know exactly what's going on there. I presume you could probably get manganese in the calcium site in scheelite, and so you could get manganese emission along with rare earth emission. But that's not what we've seen when we've done spectra on these ones. So, I mean, I think work needs to be done there. But you said something about daylight luminescence?
Well, then it's excited essentially on the blue light, the blue end of the visible spectrum. So around whatever, 400 nanometer. And that's what gives you actually this dark red color.
Well, that particular one is a mid-wave ultraviolet, and it's very good at 310. And I have I have a lot of sources of UV light here, but I mean I have 310 and 295, and both of them give about the same color. They're a little bit different. So that's not, you don't get much of that in visible in the visible light from the sun, because most of it's absorbed in the atmosphere. You get plenty of long wave UV, of course, and that will excite samarium, europium, and fluorite very nicely. And people, we've done experiments where you can take a piece of Rogerly fluorite, and you can measure the UV coming into it in bright light, and you can see that it's fluorescing in bright light, but you don't see it too well because of the sun. If you go in the shade near the bright light, you get somewhat preferential separation of a long wave UV and other radiation in the blue. And so you see the fluorescence much better just in the shade right near, like if you go into an awning near the sun, you'll see a pretty bright emission of that. If you go further away, you won't see it as bright. It's not fluorescing as strongly, of course, it's much weaker than in the sun, but the bright light of the sun washes it out when you're under that. But I haven't seen that for scheelite. I haven't seen any, well, I take it back. I take it back. The yellow emission that I spoke of during the talk is actually under long wave UV. I think that particular one is from Mongolia, and there may be a few other ones that have that emission. And so, yeah, you might be able to see that in the shade with the sun, but it's not as strong as some of these other ones, so it might be hard to see.
Okay, Ray?
Yeah, just a quick question, and other people may know the answer to this, but when you see like an afterglow when the light's gone, some people call it phosphorescence, is that the forbidden reaction going on after the exposure to light?
I have a particular stand on this issue, and other people don't agree with me. It's okay. Phosphorescence used to be the word used for what's called classical phosphorescence. And that's a transition or a process you see in organics where you have what's called a singlet to triplet transition. I don't want to try to explain what that is, but let's just say that when organic molecules, you can excite them with ultraviolet, and then they have two pathways back. And one is to go through a triplet state, and that's a forbidden state. It's very forbidden for organics. So in fact, it might take a second for it to actually get to decay down and give you emission. And it's at a different energy than the regular fluorescence. So when you get excitation of these organics, you will see blue quick fluorescence, and you'll see delayed long phosphorescence from this triplet state, which will be a different color. So the fluorescence and phosphorescence are different colors because they're from different excited states. Now, in other minerals where you have a delay, I think probably the best example is willemite from Franklin. You'll see a long delayed luminescence. You know, in my way of thinking, that's not phosphorescence. It has nothing to do with a singlet triplet state. It has to do with trapping states. So electrons are excited actually it's electrons excited in the manganese in willemite. And some of them, they don't leave the excited state. They're trapped nearby by arsenic atoms. And thermally, either at room temperature, but faster at high temperature, they're kicked out of the arsenic site and back into the excited state. And then they can decay down and give you the luminescence. So this is a process involving an electronic defect, the arsenic. That can go a very long time. If you don't have enough thermal energy, it can go for hours or days. It's very long term. But the fluorescence and phosphorescence, in that case, you want to call it that, they're both the same color because they're both coming from the same state. So that's how I differentiate these things. If the emission is from the same state, same excited state, it's the same color, then it's not phosphorescence. It's really thermoluminescence, or you could call it trapping fluorescence. But if there's a different state producing it entirely, like a triplet state, it's a different color, then it's phosphorescence. But other people don't like that. They want to call everything phosphorescence. I like to use afterglow because it was suggested quite a few years ago by Garlick and others. These are physicists. Anything you see when you turn the UV light off or the source, you call it afterglow. Then you don't have to figure out what the process is, because there's a lot of other processes. I only named a couple. There's many more processes that can produce luminescence, and delayed luminescence. So, okay, long answer, but that's my answer.
Thanks.
Okay, thank you very much, Glenn.